You're welcome to day 14 of 50 days of tutelage. And today in physics class, we're going to be talking about work, energy, and power. In our previous class, I'd introduced you to the concept of force. And now that force is an agent that tends to cause motion to happen. Now, not every time that you apply force would movement happen. That is why force is regarded to as the agent that tends to cause motion. But whenever this force is able to cause motion successfully, and this motion is done in the direction of the force, then you say work has been done on the body. And that's basically the introduction of what work is. In physics, we believe that for work to be done, there are these things that need to be in place. Number one, there is the application of force on a body, the application of force on a body, and the body moves in the same direction as the applied force. When you have the combination of all of these, then you say the body has been worked on. By what? By this particular force. But if, let's say, this body moves in opposite direction to the force that was applied, in that situation it implies that negative work has been done. However, this body cannot actually just move opposite to the direction of the applied force. It means that there are other forces that are in play here. Don't forget, like I told you already in the previous class, the what usually perform the movement at the end of the day is always the resultant force. So, and if the resultant force, if movement happens in opposite direction to the place where you apply the force, what that definitely means is that the resultant force is acting in opposite direction. And you cannot have such resultant force for just a single force. It means that there are other forces that are also in view as well. It could be friction, it could be so many other things that you are not applying. So work done generally is done in the direction of the resultant force. So the better way to put it is that work is said to be done when a force or system of forces act together and the resultant force moves the body in the direction of the resultant force. So that's basically it. So work done is always regarded to as force multiplied by distance. So, but the best way to put it is that work done is resultant force, let's call it RF, multiplied by distance. So, anytime you want to find work done on a body by a force or by several forces, the first thing you need to always do is to find the resultant force, And I know that there are times that they will you would have seen maybe a particular force is acting on a body that is resting here, and this force is acting at an angle, let's say theta. So automatically, what they will just say is that work done is FD cos theta. But can work not also be FD sine theta? It can actually be FD sine theta as well. So the idea is that you need to resolve the force in the direction of motion. So for this particular case now, if you're going to be dragging by this force, so this is like a force that is dragging this object, obviously this force is not acting to lift the body upward. So upward motion is not going to happen. So that means that motion is going to happen in this direction towards the right. So since that is the case, then you resolve this to the horizontal. And when you resolve this applied force to the horizontal, it becomes F cosine theta. And that is where you have that work done. So using this that I said earlier, resultant force is what? F cosine theta multiplied by distance. So you can now multiply FD multiplied by cos theta. But like I said, it can also be sine theta, and the case where it will be sine theta is if the force, the angle of inclination rather, is given to the vertical. So for instance, let's say in this situation you have this resting on the floor, then you have this, then you have your force acting like this. If the angle theta is here, by the time you resolve to the horizontal in this case, when you resolve to the horizontal in this case, you're going to get F sine theta. So work done can also be F sine theta multiplied by D. So the only time it is F cos theta multiplied by D is when the angle is made with the horizontal. So you need to go to the previous videos to learn how to actually resolve forces from different components and all of that. So another thing again is that in this situation, if you have to find work done, maybe this body moved a certain distance D, And then you have to find the work done on this body. And let's say this surface is not a smooth surface, it is rough. That implies that there will be friction in opposite direction like this. So if you want to find the actual work done on this body, then you have to find the resultant. So the resultant force in this case is going to be F cosine theta minus the frictional force. So whatever result that you get here is what you multiply with the distance, and that's what will give the work done. That is why we also have the concept of what we call work done by friction. Work done by friction. So in the case of work done by friction, if you multiply this by distance, so if you say work done equals resultant force multiplied by distance. So in this situation, you are going to have F cosine theta minus frictional force multiplied by distance. So if you expand the parentheses, you're going to have Fd cos theta minus F frictional force multiplied by d. So in this situation, this component, the component here is the work done by friction, and the component there is the work done by the applied force. So sometimes when you apply a certain force at an angle, you are expected to get a certain work. You're expected to get a certain work. Let me write that properly. You're expected to get a certain work, but the presence of friction diminishes it such that the work that you get eventually is going to be a lesser amount of work than the expected amount of work. So friction tends to reduce how much work that is done by a body, by a force being applied on a body. So that's basically the introduction to what work done is. So without movement, work is not said to be done. So as a physicist, if you're a physics student, if somebody is carrying a particular load on their head and they carry it for, like, let's say 2 hours, 3 hours, and they are sweating at it, as far as that system is concerned, so let's say this is the body and they're carrying this load on their head, so I'm sure they can't be happy. So they cannot be happy. So if they're carrying this load on their head, they have not done any work. No work is done by this body because there is no movement as far as it's concerned. So the only time they had done work was when they were carrying this thing up. So now that leads me to the concept of what we say work done against gravity. Work done against gravity. So you can do a work in lifting an object up, and you can also do a work in bringing an object down. Or you can even let the body just fall freely like that. So I'm going to show you what that means. Like I said, work done is resultant force multiplied by distance. So let's say you want to lift an object up. If you want to lift an object up, what you need to do is to be able to, first of all, overcome the weight of that object. And for you to overcome the weight of that object, you need to apply a force that is strong enough to overcome the weight. So in that situation, the resultant force is going to be the weight of the object. So you have mass times acceleration due to gravity. Then distance in this case is going to be the height from the ground upward. So it's going to be the height from the ground upward. So therefore you have h. In this situation, I know this looks familiar, especially it is something I'm going to talking about soon. This looks familiar, but I'm going to establish a clearer point of view when I get to energy. So quickly, let me move to energy like that. Now, contrary to work, there is also energy. These guys, work and energy, they are of the same dimension. In fact, they almost mean the same thing. The only difference is that work is action. Work is action, and energy is more like capacity. So work is the action. Energy is the capacity to perform the action. So when you say somebody, let's say somebody can actually like take 10, maybe somebody can break 10 coconuts with their bare hand. Yeah, 10 coconuts with their bare hand. But at a given period of time, they decide to break just 4 coconuts. In this situation, the work that they have done is 4, but their capacity is 10. In fact, that also leads us to another definition that work is actually dissipating of energy. Work is the dissipating of energy. When you begin to let the energy out, then you say you are doing work. So the fact when you spend energy, what you are doing is actually working. So the amount of energy that you have dissipated will be the same thing as the work that you have done. So work done dimensionally is the equivalent to energy. The only difference is that work is action and energy is capacity to perform the action. That is the capacity and the ability to be able to do this work. That is what it is. In fact, we have what we call work energy theorem. Work energy theorem, which I'm going to state for you later on in this video. So now that I've defined energy, we have different types of energy, different forms of energy. But the one I'm going to be talking about here is going to be the mechanical energy. So we have the mechanical energy. Mechanical energy. And this mechanical energy, there are two of them. We have the potential energy and we have the kinetic energy. So one misconception about potential energy is that potential energy is the energy possessed by a body at rest. That is one of the most wrong things that you can ever come across or you can ever hear in your life. If you have heard that before, that potential energy is the energy possessed by a body due to its state of rest, that is very, very wrong. So what is potential energy? Potential energy is simply the energy possessed by a body by virtue of its position. By virtue of its what? Position. So if it is not because the body is at rest, that is why the body has potential energy. It is by virtue of position. And what is the concept of position? This concept of position is always being traced from a sort of origin, a sort of reference point. So, for instance, we have what we call gravitational potential energy. So, the reference point is always the ground level. The reference point is always the ground level. Therefore, any object that is positioned at a certain height above the ground, at any height above the ground, they will always have gravitational potential energy. So what does that mean? This object might be moving. So for instance, an object that is falling down, and this is still the ground. If an object is falling down, it is falling down like this, it is falling down like this. It is obvious that at this point, the body is still moving. But guess what? The body still possesses potential energy. It still possesses potential energy because even though it is moving, it is still at a certain position above the ground. Now, we also have elastic potential energy. You see, when let's say this is an elastic material and at this point it is at rest. Now, if you have an object here at this particular point now, if you place it here, nothing is going on. So you have this body is at rest. But you see, the moment you stretch it, the moment you stretch this thing, before release, by virtue of position, it is some distance away from the state of rest, from the original length, from the unstretched face of the spring or of the elastic material. Now, it has now been displaced at a certain position away. You see, at this point, it possesses what we call elastic potential energy, and that is how your catapult work. What happens is that when you stretch your catapult, so permit me to just draw this catapult anyhow. When you stretch a catapult, let's say this is the stretched state now, what you have done is that you have made it possess elastic potential energy, and when you release it, it's able to do a certain work. Energy is going to be dissipated. So and potential energy is the energy possessed by a body by virtue of its position. So that position is what I just explained now. That position is talking about a relativity to the a reference point based on the kind of potential energy we want to talk about. Now, what about kinetic? Is by virtue of its motion. Energy possessed by a body by virtue of its motion. So it is possible for a body to possess both kinetic energy and potential energy. So these two guys are not opposite of each other. In fact, they are complementary. They work hand in hand, which is why at every point in time, when you have a potential energy, then there is a possibility of having kinetic energy. In fact, at all times, we always consider what we call total mechanical energy. total mechanical energy, and this is the sum of potential energy plus kinetic energy at all time. Is the sum of potential energy plus kinetic energy. But here's what happened. At some point, potential energy decreases and kinetic energy increases. Also, when kinetic energy decreases, potential energy will go up. So the two of them are always acting to cancel each other out. So one goes up for the other to go down, that and vice versa. So, and there are times that they can be equal as well. So let me use this scenario as an example. I want to use gravitational potential energy now. So let's say this right here is the ground level, and then you have an object. This object is at this position above the earth. Now, before it starts moving, it is at a particular height above the ground. So at this height above the ground, what happened is that at the top here, the total mechanical energy is the addition of potential energy plus kinetic energy. But because it is not moving yet, so it does not have potential energy. So therefore, total mechanical energy here is potential energy. And then let's say it get to the point here, it get to this point, to this midpoint. It's still at a certain height. So let me make this capital H, and then let me make this small h. Now, it's at this point now, its total mechanical energy is still going to be PE plus KE. But in this case, it is not purely PE alone. It is both PE and what? And kinetic energy. Why? Because there is also movement involved. Now, when it gets to this point, just a point before hitting the ground, it attains what we call maximum velocity. It attains what we call maximum velocity, and it has done so much work. It has done a work that is the same thing as the energy that was stored in it at the potential stage. So in this case, total mechanical energy, which is still PE plus KE, is now purely kinetic energy. But here is the thing. Law of conservation of mechanical energy says that the total mechanical energy is always the same at all time. What does it mean? So let me call this one PE up, PE middle, and let me use for the total mechanical energy instead. Total mechanical energy up, total mechanical energy middle, and total mechanical energy down. So what we're saying is that total mechanical energy up is the same thing as total mechanical energy in the middle, is also the same thing as total mechanical energy at the down part. So let's call this one 1, let's call this one 2, and let's call this one 3. So what that implies is that PE1 is the same thing as PE2 plus KE2, and is the same thing as KE3. So take note of that. The potential energy that you started with is the same as the sum of the potential energy and the kinetic energy at any point in the middle, intermediate point, and it's also the same thing as the kinetic energy at the down point in this place. So in this place, the potential energy has totally been converted to kinetic energy, and this is the model that you should always work with whenever you are dealing with this problem. So now let me talk about work energy theorem. So what is the work energy theorem? Work energy theorem is, in summary, is simply that work done is change in kinetic energy. So in this case, I've not given you what kinetic energy is. Kinetic energy is given as half mv squared. It's given as half mv squared. M for mass, v for the speed of the body. V for the speed of the body. Now, the work energy theorem says work done is change in kinetic energy. Don't forget what we have learned earlier. We said that work done is resultant force times distance. So let's see. So if work done is change in kinetic energy, that is work energy theorem, then that means that we are talking about final kinetic energy minus initial kinetic energy. And so that implies that we have half mv squared minus half mu squared. So you remember when we were doing motion, I'd already shown you that v represents final velocity and u represents initial velocity. So we are putting it in the context of kinetic energy now. So this is going to be equal to, now you can see that half and mass, they are both constant. So that is half m multiplied by v squared minus u squared. And this is going to be half m. Now, from equation of motion, if you remember your equation of motion, I said that, sorry, equation of uniformly accelerated motion, I said that v squared equals u squared plus 2as. So what does that imply? That implies that v squared minus u squared equals 2as. So I can easily replace this v squared minus u squared with 2as. And then 2 cancels out. And what do you have here? MAS. What is MA? That is your resultant force multiplied by what is S? Your displacement. So you can see that work done is change in kinetic energy. Work done is change in kinetic energy. And that is what the work energy theorem, that is what it states. So I've been able to show you the transition between work energy, mechanical energy, potential energy, and kinetic energy. I've been able to show you all that. Before I go to power, because power is just the rate of doing work, and the major part of power is to understand energy and work done. Once you understand these two guys, then power is just easy peasy. It's just a rate that we calculate over time. So if you have a simple pendulum here, and then you release it at first, what happens is that it's going to swing. So this is the point where you release it, then it starts swinging and it's going to and fro. So you notice that at every point in time, when it gets to this place, it takes a momentary stop. And then begin to fall down again. And you see that at this middle point here, there is no stopping at all until it finally comes to rest. So what happened here is that in this place, potential energy is maximum. So at this extreme, potential energy is maximum. And this place, kinetic energy is maximum. So when kinetic energy is maximum, potential energy is zero. When potential energy is maximum, kinetic energy is zero. And that is that about that. So finally, let's talk about power. What is power? Power is simply the time rate of doing work. Power is the time rate of doing work. So in other words, work over time. So note, sometimes we use the formula for energy. The only reason why we do that is because we regard work as energy being dissipated. So if you have been given the energy that is being dissipated, then you can easily use it here. So power is work done over time. Power is work done over time. So you can always manipulate your way around all this formula. So work done is PT, power times time. You can always manipulate your way around it like that. And so that's it for today. Of course, there is efficiency, but I don't want to talk about that. It will be covered when we do machine. It will be covered when we do machines. I mean, simple machines and all of that. But just a form of bonus before I leave, efficiency is the work output divided by work input multiplied by 100%. So work output divided by work input multiplied by 100%. And that's it for today's class. Don't forget to like, comment, and subscribe to the channel if you have not. I'll see you in the next one.